Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today I'm going to finish off general relativity. So, last time we discussed the nature of the principle of equivalence and how the inertial mass equals the gravitational mass, and that became the starting point for Einstein's idea about general relativity, where he then posited that all freely falling frames see the same laws of physics. So if you're in a uniform gravitational field and falling, you feel the same laws of physics. Everything about the laws of physics is the same as if you were way out in space, seeing just floating in space far away from any kind of gravitational source. So what this means is that we're going to have to change what we mean by our relative terms, how we observe that distant person doing things in that distant frame. Not how you do things inside your own frame, because I could be in a freely falling frame in this room. I could be accelerating in this room upwards in a spaceship and going out away from, far from any star, far from any planet, just in a room that has rockets associated with it. And I would still have all the laws of physics being absolutely identical. Okay, so what we have to look at then is that mass then, it says, what does mass do? Mass causes other mass to accelerate it when there's other mass near it. That's what we call gravity. But special relativity says that distances and times are measured only between uniform frames, and but distances and times are intimately linked. But when special relativity is talking about, we're talking about uniform motion. So one frame moves uniformly next across to another. They're not turning around each other. They're not accelerating or decelerating past each other. They're uniformly moving. So general relativity then says, let's have non-uniform motion because a freely falling frame accelerates as it falls. So we can say that the geometry of space-time in special relativity is, quote, flat, and the geometry of general relativity is, quote, curved. So curved space-time, flat space-time, let's see what we mean by that and see some of its results. All right, so Newton found Newton's ideas lead to the idea of the least action principle. And the least action principle, according to Newton, because of a universal clock across all of space and time, across all of space, is that there's one clock. So Newton's least action principle said that any two objects between any 2 points, when an object moves from here to here, it does so in the least amount of time, if it's freely falling. And if it's under it, it doesn't matter what it's doing. It always does so in the least amount of time. So in space-time, when they're relative, Einstein noted that the only way you have to change the nature of the least action principle to say that objects move along the shortest paths between 2 points in space-time. Not that minimizes time, but minimizes the length of the path in space-time. Notice how Newton is just they minimize the length of time. But you can take any path you want, but the forces that are acting independently or dependently will force that thing to move along in the shortest path in time. But when you look at space-time, you then have to say how space and time intermingle and objects move according to the shortest path in space-time. Space and time as a unit. So because now we're talking about space-time, we inherently drag in the concept of geometry because we use the word space. So space is a measurement, space is measurement of left, right, backwards, forwards, up, and down. So geometry is always that measurement. So now actually another way we can think about it is that geometry then, how do we extend geometry so we include the concept of time? And that's the concept of space-time. So Newton, of course, went through this idea of a universal time. But Einstein got rid of that and said that there is a space-time as linked and they're intertwined with respect to each other. All right, so then let's see what we mean by the shortest path. So the shortest path in a flat space-time is kind of obvious. Well, let's say you have some object that's got a pointy direction thing. You say, well, let's make an object that goes around in a box or something. So let's make a closed path. I take my pencil and I move left, right, backwards, forwards. But I'm always keeping the pencil pointed in the same direction. In a flat space-time, on any flat surface, I could do this on the surface of a table, as long as I take the arrow or the pencil and I simply transfer it little by little, such that each time I move from here to say here, I make sure that the pencil is pointed in the same direction as when I started here, and I move the pencil to here, but I keep it pointed in the same direction. So we're going to work with that as an idea. So let's keep the idea that we're going to move this pencil by keeping it going in the same direction. All right, so a curved path might be like, whatever it is, but a curved path through space-time is very similar to a curved path on a spatial object. So now I'm going to use my globe, because I came to the lab for that reason. I'm going to say, what happens if I'm going to put this pencil on the surface of the globe, let's say here, and now I'm going to do what I did before. I'm going to move it across, and I want to end up back over here. And what happens when I do that? So first of all, I move it little bits at a time north, so that it's always pointing in the same direction, right? I'm staying on a longitude line. I move all the way to the North Pole, and then I stay, and now I move directly south, and I keep the pencil pointed by, this is a very large, small globe. So, but if I was on the surface of the globe, I could walk it so that it always seems to be pointing south. But notice what's happening is that the direction of the arrow, the vector, the pencil, is changing. And so then now when I parallel transport it, ooh, nice big word, all the way back to the original location, you'll see that the pencil is rotated. So I started here, moved up, moved down, moved across. And every step of the way that I did on the surface of the Earth, let's say I really did this, really marched it all the way from the equator, all the way to the North Pole, all the way back down to the equator, and all the way across, I will have rotated it 90 degrees. I mean, I could just go up, move it straight down, and then move it across. And I've parallel transported it. So parallel transport is a funny thing. It means that no matter what, I'm going to take this thing, it's not just a location, it's a direction associated with that location. And so I'm going to try to move this little arrow around the globe as I go. So as I move it around the globe, if I'm in Canada, and I keep walking it, I'll just walk like this. I'll say, oh, okay, I'm going to walk my pencil like this all the way down to the equator. And as I walk it, I'm always going to keep it pointing the same direction. But no matter what I do, I'm walking on a curved surface. So the curved surface itself changes the orientation. So that when I finally get back, and so when I get to the equator, so I'm standing at the equator, and I want to make sure that the pencil stays pointed in this direction. But I know I've got to go west. So it's like, okay, the pencil stay direction that way. So then I move left, because I keep the pencil pointed. See what I did? So I start here, I move up, I move over, and I move down, and I move back. 1, 2, and I move up, down, over. So as I do those motions, I always keep in touch with the direction of the pencil. So if I move up, down, over, notice I've rotated it again. So what happens is that we can think of curvature in space-time as the failure for walking around a path to come back to the same orientation that you were when you come back to the place you started from. So if you take a closed path in a curved space and try to stay focused in the same direction, try to always go in like this direction and always keep something pointed in that direction as you walk inside that and make a curved path, a closed path in that space, you'll rotate a little bit. And so that's how we actually measure curvature in space. If you wanted to measure, say, the curvature of anything in space and time, you then say, okay, I'm going to parallel transport this thing here, and then when I get there, I parallel transport it across, and I parallel transport it back. But notice in a flat space, it stays flat. So general relativity in a freely falling frame, inside the freely falling frame itself, you don't see any rotations, right? Because all laws of physics are the same inside a freely falling frame. But outside the frame looking, you see that the person's accelerating, which means there's changes. So if I watch somebody freely falling in a gravitational field, I would see the effect of these rotations inside of there. There would be fictitious forces that I would see as I watch the person fall. But inside the frame, I'm not going to see any difference. I'm going to move my pencil around in this box and I won't see anything. because I'm freely falling with the frame. Outside, I'll see something different, relativity. All right, so parallel transport defines curvature, and that's the thing that we use to when you cannot parallel transport it back to the original orientation, when you make a closed path, then you have curvature in space and time. Now, the funny thing is that even though it fails to come back to the same orientation, remember that's the straightest possible path in terms of space-time. When you make that change, Einstein's least action principle says that that's the path you got to take. And so since it's the shortest possible path, that curvature plays a part and changes orientations. So what does this mean? It means that if you were to ask Newton about this, Newton would say, oh, hey, that's not a big problem. Mass deflects the object from its direction that it's going because of the force due to gravity. And so there's an acceleration. And so since there's a force due to gravity, you change the orientation that it's going, and therefore it follows a curved path due to the force due to gravity. But here's what Einstein said. Einstein said, well, wait, in a curved space, you don't have any forces. You're simply following the shortest possible path through that space-time. And if you're following the shortest possible path through that space-time, there is no force. That's what we mean by the equivalency of falling frames. The equivalency of falling frames means it doesn't matter if you're falling in a gravitational field or out in the middle of space. It doesn't matter at all. You're always following the shortest possible path through space. So mass then tells, we can then say that it's not really a curved path. There are no forces. Einstein abolished the idea of the gravitational force. There is no force. You're simply following the lay of space-time, the lay of the land. It's a different way of thinking about it. You must accelerate in your speed as you fall in a gravitational field because space and time is curved in the direction that you're falling. I feel the weight on my feet because I am falling in a curvature. I am continuously falling towards the center of the Earth. Why am I falling? Because space-time is curved by the Earth, and so I am therefore falling towards the Earth. Why do I feel my weight? It's because the floor pushes back up on me. We're still using Newton's law in that way. And so there must be a force to resist that fall. And so my legs push up against the floor, push down against the floor, and the floor pushes up against my legs with equal and opposite force. That's Newton's law. We keep that. But the idea is that now we have effectively abolished the force due to gravity by simply changing this curvature of space-time, and you simply follow the lay of the land or the lay of space-time, and that gets you to where you need to go. All right, so this leaves a lot of hang-ups because people, when they talk about space-time, they get all hung up about it and they say, well, it's not really curved. It's like, no, but you have to add in the concept of space and time. Because Newton's laws assume a universal time. But we already know that when you talk about relativity, space and time are interlinked. That's what special relativity showed us. Now the addition of mass simply adds to curvature of space-time. So therefore, John Wheeler quoted the famous quote that everybody always says, and that mass tells space-time how to curve, and curved space-time tells mass how to move. And we always say then, okay, well, what's it curved into? It's like, you could posit an extra spatial dimension, if you wish, in order to accommodate this curvature. That's fine. Many relativists do that, and they call that the bulk. And so therefore, well, we can't perceive that bulk space. We only perceive it in the sense that we are falling into it in a very strange way. So that's our perception of it, because as the curvature flows into the bulk, which would be the extra spatial dimension, that's what's posited in any event, or at least one way of explaining it, is that you fall towards this towards matter curves into that extra spatial dimension. Well, but however, if you look at the actual mathematics of, like, from any standard general relativity textbook, you don't actually need that extra spatial dimension in order to explain curvature, because you can create a mathematical space that has curvature but doesn't have a radius of curvature inside an alternate space. That way you can have arbitrarily curved spaces. So you basically do measurements of path lengths inside of this space-time. And so you find the shortest path lengths inside of this space-time. and you have to divest yourself away from the concept that a coordinate system is the same thing as the distance. So coordinates in a space-time can be deceptive, meaning one step in one direction could be longer than a step in a different direction. So steps are simply coordinates, but their actual path length may be longer depending on the curvature of space-time. So that kind of helps a little bit about it. But really what we have to think is the nature of general relativity simply says that we no longer need a force due to gravity. Because remember, Einstein said that the force due to gravity accrued to Newton. Newton's force due to gravity is instantaneous. It goes across the entire cosmos instantly. But in order to take care of that, we instead use curvature of space-time, which allows then the propagation of changes in space-time. So that leads us to the next bit, which is tests. Okay, this is a great idea, fine, we can play curvature, makes the mathematics a little more complicated, but yet it then explains what Newton said he could not explain. Newton said, I have no idea why gravity works the way it does, it just seems to, and I have no idea why inertial mass is the same as gravitational mass, they just seem to be the same. Einstein said they are the same, and the reason for the agent is simply the curvature of space-time. So you use the two problems that Newton said, well, I don't know what they are, and you start with them as postulates, and that gives you general relativity. All right, so this is a great idea, but what does it predict? If you combine space-time and you combine them together, the first thing I talked about last time was the precession due to precession of Mercury's orbit around the Sun. And we found that that Mercury's orbit is about 574 arc seconds per century. That's what's observed, but Newtonian mechanics only gets 531 of those arc seconds per century, and so there's a discrepancy. And people throughout the latter part of the 19th century were trying to figure out ways to tweak Newton's laws. But when Einstein came up with general relativity, he said, wait a second, let's take specifically Mercury's precession. You solve the equations according to space-time with the Sun here and Mercury there, and guess what? The 43 arc seconds that are required fall directly out of Einstein's equations, and you get the exact 574 arc seconds of change. That is a direct result of general relativity. You don't have to change anything, you get what's observed. All right, that's pretty cool. So what's observed can be explained by the equations. That's nice. But then remember, Ptolemy's equations explained the observations, and they were kind of twerky. So we don't really care. That's not really the best way. We want to say, all right, what does Einstein's theory predict that can then be observed? That's a better thing. So the Einsteinian theory of general relativity predicted that space-time is curved around stars, because stars are massive, and the Sun is a star. So we should see actually the change in trajectory of light, or the apparent bending of light, because the path through space-time near the Sun is different than the path through space-time far away from the Sun. So the Sun changes the path that light takes. So when we look at something that's going towards the Sun, that comes by the Sun, we would see it actually to be in a different place in the sky. So it was a prediction that the stars surrounding the Sun at a total solar eclipse in 1919 would actually show different positions in the sky. They would be farther apart from the Sun than they were when the Sun isn't there. So what Arthur Eddington did in 1919 is he sent an expedition down to, I believe it was South Africa, to actually watch the solar eclipse. And they went down very early to take pictures of the sky, of what the stars look like, without the Sun in front of them, the Sun and Moon in front of them. They waited a few months for the Sun to get to the same position in the sky where the solar eclipse was going to be. And what did they see? They saw the stars spread apart because the light that was going, so the stars were coming directly to them. But then what happened is that instead, light that is going in this direction, a little farther apart, then gets pulled back towards us. And so when we look at it, the angular separation of the stars widens as opposed to narrows. So the position of stars in the sky was predicted to be apart, and the amount of that prediction was predicted by Einstein and observed by Eddington in 1919. And subsequent to that, Other applications like starlight positions of spacecraft have to be checked because if they're on the far side of the sun, say they're on Mars or something, on Jupiter, you have to take into account general relativity in order to see where they are in the sky. And other eclipses have shown this as well using radio astronomy because it's a little easier to look at radio sources behind the sun because the sun is not as loud in radio, and so it's also easier to observe. So this has been observed again and again, and it led to a famous quote when it was observed in 1919, and reporters asked Einstein what would happen if Eddington had not seen it, and he said, well, I would pity God for the equations are correct. And that was an interesting thing to say. So another things that are predicted by general relativity are gravitational arcs. So if you have a galaxy that's very, very distant and another galaxy that's in front of it, the light from that would pass around and be distorted, and you have a distorted image of a galaxy that's in the background with respect to a foreground galaxy. Those things have been observed by the Hubble Space Telescope in SCADs, lots of galaxy clusters where there's a huge mass of galaxies, and the light from background galaxies gets distorted and changed into strange shapes. Which then you can think about, you can reconstruct the original appearance of the background galaxy in just the same way that an ophthalmologist can reconstruct what eyeglasses to give to you because the gravity of the foreground cluster acts as a lens. All right? That's another prediction. A further prediction is that if a body is rotating, like the Earth or the Sun is rotating as a massive body, then space-time itself is dragged along with that rotation, which is a really weird concept. It's called frame dragging. And this prediction was a long time coming, and it was finally observed by the Gravity Probe B, which was basically a perfect gyroscope that orbited the Earth. And the prediction from which how the gyroscopes would change with respect to time due to the rotation of the Earth. As the Earth rotates, it drags space-time around it with it. And that there's a certain amount of dragging that was expected. Basically, the satellite was trying to point to this this direction, and the gyroscopes in it were dragged a little bit to the side, according to, as the Earth rotation, the orientation of the gyroscopes inside the spacecraft was changed. So Gravity Probe B, it took 5 years of data. After it deconstructed it, actually discovered this frame dragging effect, which is predicted by Einsteinian relativity. Next, this was like about 5 years ago, but in 1974, another major prediction of it is that if you have two massive bodies that are close to each other, really massive, and they're orbiting each other as a binary pair, then they'll actually the rate at which they orbit each other will decrease, and they'll get closer and closer and closer and orbit faster and faster and faster. And Hulse-Taylor found, using a radio telescope at Arecibo in 1974, a pair of pulsars, neutron stars, which we'll talk about later. These neutron stars are orbiting each other, and the rate at which they change their orbital period is a direct prediction of general relativity. So general relativity predicted this behavior, and it was observed around this kind of object, but how were they changing? Well, the change happened because the prediction of general relativity says is that the change in space-time, meaning the instantaneous problem that Einstein talked about originally, is that the change in space and time due to the motion of objects has to spread out and it can't go instantaneously. It has to go at the speed of light. And if it goes at the speed of light, by the time something moves over here that's really massive and moving very fast, then there would be a gravitational wave. A wave in space and time. A disturbance, if you will, in space and time, propagates outward. And that radiates energy away, which allows the two neutron stars to get closer and closer together, and their periods of orbit change. And that's a direct prediction of general relativity, and that was observed in 1974 by Hulse-Taylor. And for it, they got the Nobel Prize in 1993. And finally, well, actually, I think we got one last really good one. In September of 2015, the LIGO group, after 30 years of work, discovered gravitational waves that were due to the collision of two black holes. And the gravitational waves happened in a similar way to Hulse-Taylor, but as the final in-spiral of two massive black holes that stretched and squeezed space-time, and these waves propagated out through space and caused the detectors to literally squish and stretch and squish and stretch by the tiniest amount, an incredibly small amount at the distance we are from them. But the distance we are from them, it gives still, even though they're distant, the way in which the detectors stretched and squished had a prediction. According to general relativity, according to the merging of two black holes, you would see this, and that's what they looked for, and that's what was observed. And so this is apparently yet another major confirmation of general relativity. And finally, just to finish off with something more prosaic, when you drive your car, you have these satellites above you helping you get directions, either through Siri or through your Droid or what have you, or your Maps phone, your map app. And guess what? If the general relativistic corrections were not put into the software for your GPS system, doesn't matter what's doing it, if those general relativity corrections, due to the light travel time, due to the fact that the Earth has gravitational effects all around it, then guess what? You would lose your location on the surface of the Earth by about a mile after about 15 minutes. So you have to take into account general relativity in order for the global positioning system to work. So all of these things go together, and all of it is premised on the concept that space and time are the same, that mass and energy cause curvature of space-time, and curvature of space-time is the explanation for this feeling that we have that we call weight. It is and it also explains the nature of the acceleration that we feel due to gravity, and it gets rid of the need for a force due to gravity. It is simply the curvature due to gravity. But so we don't necessarily have to drop all of Newton's laws, because general relativity, I talked some pretty extreme environments like Newtonian physics, neutron stars and black holes. But this leads us to what we call the correspondence principle, is that any theory that replaces a previous theory, it must incorporate all the observations of the previous theory, or find a space in which that works. So when we look at Newton's laws, so Kepler came out with his 3 laws of motion of the planets, and they were correct for the sun and for the planets. Well, when Newton came out with his laws, he was able to explain all of Newton's laws and also expand upon it to see how other stars might behave. And that allowed it to predict the location of Neptune. Kepler's laws couldn't predict Neptune, but Newton's laws could if you saw disturbances inside or discrepancies. So Newton's laws had Kepler's laws in them, but they expanded and allowed us to do other things. But Newton's laws had their problem areas, and Einstein's laws came along. Einstein's theory of relativity came along and said, well, if we apply this idea, in the slow regime, meaning speeds not close to the speed of light, and not an extreme curvature of space and time, not near supermassive objects, and not going very fast, then general relativity becomes Newtonian mechanics. And in fact, that's why we don't throw out Newton's laws. They're still useful. They're incredibly useful. But if we want to actually measure using a GPS our location to a couple of feet as opposed to a couple of miles, if we want to get a spacecraft exactly to a location on Mars, if we just want to get it to Mars, Newton's laws are great, to within a couple hundred miles. But if we really want to get to a specific location in Gale Crater right next to this place, then we need general relativity. So relativity encapsulates or holds Newtonian physics, and Newtonian physics holds previous things, but notice they supersede other things too. Like Newtonian laws and Kepler's laws superseded Ptolemy's laws. Well, Ptolemy created the geocentric model, right? Now, his mathematics was extremely complex, and it had flaws. It could not correctly predict the phases of Venus, but Newton's laws could. So we discard all of Ptolemy's laws. Now the funny thing is that if we wanted just to simply know the positions of things in the sky, Ptolemy's laws were very complicated but useful. And that's why they were used for a long time, is they were useful. But once we get to something, we're going to go past usability and into explanation and find explanations for deeper and deeper and deeper and finer ideas and finer observations and corrections to problems. Then we have to go deeper and deeper theories. So the essence of general relativity is that so far it has been unchallenged. And people have looked for discrepancies between the inertial mass and the gravitational mass and have found none. It's one of the best recorded things, or the best measured efforts, because when you say this is a challenge. And people say, okay, I'm going to prove you wrong, Mr. Einstein, because if I can prove you wrong, I'm going to get the Nobel Prize. But the funny thing is that general relativity keeps coming back. And every test, the test of the equivalency of the inertial mass and the gravitational mass, keeps coming back as positive. They're the same thing. So this postulate is testable, and it stands up to tests. So we have great confidence that general relativity is a very good approximation for what the universe really does. And that's going to have implications when we talk about cosmology, when we talk about black holes, we talk about neutron stars, lots of things that happen in astronomy as a result of general relativity. And we'll all talk about those things soon as we come along in the course. So we'll see you next time.